In this video, I want to take a look at how we can solve homogeneous constant coefficient problems. These are going to be the basis for all of the higher order differential equations that we're going to look at going forward. So once we know how to solve these, this is going to be the starting point on almost every problem we look at for the next several weeks. So what is a homogeneous constant coefficient problem? An example of this of in this case, second order homogeneous constant coefficient problem looks like the following. It looks like a times y double prime plus b times y prime plus c times y equals 0. The fact that we have all of these terms over here with our y prime, and our y double prime, each of them being multiplied by simply a constant, so we make that totally clear. In this case, a, b, and c are constants. That's what makes it a constant coefficient problem. The fact that it's equal to 0 on the right-hand side is what makes it homogeneous, and then obviously the fact that the highest derivative is a second derivative is what makes it second order. So this is going to be the type of problem that we're going to be trying to solve going forward. But before we try to solve a second order version of this, I want to take a look at the equivalent if it was just a first order. So before solving the second order version and higher, so before solving these higher order ones, let's solve first order version. And the reason is that if we solve a first order version with the techniques that we already know how to use, we can get some insight into what the solution is going to look like and maybe use that as a guess that we can then use to kind of extrapolate to these higher order problems and solve them. So instead of me just telling you how to solve them, let's motivate how we're going to solve these by solving an equivalent first order version. So the first order version of the same problem might look like the following. It might just look like ay prime plus by equals 0. So again, the coefficients are just constants, but now the highest order term is just a first derivative, hence making it a first order problem. So how would we solve this? Well, this is a linear first order problem. We have a couple of techniques that we can use. We could do integrating factor on this, but it's also something that we could basically rearrange and solve as a separable equation. So let's just see what this looks like. If I rearrange this, I'm going to divide both sides by a, and I would get y prime plus b over a times y equals 0. And then let's move this term over to the other side of the equal sign so we can try to separate things. I'm going to move this over to the other side, and I'll get y prime equals negative b over a times y. And to clean this up just going forward, and it'll make more sense in a little bit why I'm going to do this, but I'm going to just call this some new letter. Instead of, this is just a coefficient, right? B was a constant, A was a constant, so their fraction is some other constant with the negative sign in front of it. I'm going to call this term right here M. And so what this equation really looks like at this point, cleaned up, is just y prime equals M times y. This has solutions that we can find fairly easily, again, using separability or using an integrating factor. But I've set it up so that we can solve this using separability. So solve using separability. So we've got that y prime equals m times y. If we keep in mind that y prime is really the same as dy dx. Now we can see explicitly the separation of the x and the y variables. I'm going to multiply both sides by x and divide both sides by y. And our equation looks like dy over y equals m dx. We can integrate both sides. And on the left, I'm going to get the natural log of the absolute value of y. And on the right, I'm going to get basically mx plus some constant c1. And now we solve for y with just a little bit of algebra. Get rid of the natural log by exponentiating both sides. We can drop the absolute values because when I exponentiate this, e to anything is always going to be a positive value anyways, so we can basically treat this as y equals e to the mx plus c1, which can be rewritten as some new constant c2 times e to the mx. So basically, for the sake of ease, we can leave the c in there for now. Let's just say this is c2 e to the mx. There's our solution. So this is the solution to this differential equation, which is equivalent to this differential equation under the assumption that the value of m that we're using is negative b over a. So you could write this as e to the negative b over a times x if you wanted to go back to the original variables and constants from the original problem. But the point is, this is the form that it takes. I don't actually care about the a and the b, I care about the form. What if we had simply guessed this form from the beginning? So basically what I'm saying is, instead of going through the solution techniques that I just did, the ones that we've done in the past, what if we just said, okay, I expect that our solution is going to take the form of y equals e to some constant times x. Which kind of makes sense here, right? We basically, when we get it into this particular form, we're looking for, okay, what is a function where the derivative of that function is equal to the original function, just mod some constant, so multiplied by some constant here. And yeah, exponentials make sense. So that's kind of the idea. So what if we had just guessed this from the beginning? We could plug it in to the original differential equation and try to figure out what m should look like. So basically, let's try, what I'm suggesting is, let's try y equals some constant times e to the mx as a solution to the original equation that looked like this, ay prime plus by equals 0. So basically, I'm going to need both what y looks like and what y prime looks like. So again, if this is what y looks like, then what is y prime going to look like? Well, y prime will just be c times me to the mx. If we sub these in, we would get a times y prime. Right, so I'm subbing them into this, a times y prime. So a times this, a times cm e to the mx, plus b times the original y, b times y, and here's y. So b times c e to the mx equals 0. So here's the first important thing. As soon as I plug into this, I can immediately divide by c and get total cancellation, which is nice because it means I didn't ever really need the c to begin with. It can immediately cancel out of the problem because it's a homogeneous problem. When I divide by it, it's not going to affect this 0 over here. So basically, what I'm suggesting is in the future when we try plugging in something like this, we don't need this constant out here. It's always going to cancel out. But let's see what else we've got. How am I going to make this all go to 0? The other thing that we can see, so right now I have basically am e to the mx plus be to the mx equals 0. So let's keep cleaning it up. I can factor out this exponential, e to the mx, and what's left is I have a times m plus b equals 0. So if this is equal to 0, this product of this exponential and this binomial term that we have in parentheses here, that means that one of the two has to be equal to 0. And the exponential can't be 0 because by their very nature, exponentials are always non-zero. If you think of the graph of e to the mx, regardless of the value of m that you pick, it's going to look something like this. Or potentially, something like this if it's negative. Try to do that a little better. It approaches 0 at these extremes, but it's never equal to 0. So what I'm suggesting is, let me delete this real quick. This part can't be 0, but if this product is 0, that means that this part has to be 0. So AM plus B has to be equal to 0. What does that mean M must look like? So solve for M. That means that AM is equal to negative B, and we can divide by the A to get that M is equal to negative B over A. Incidentally, this value of M is the exact value that we used in our substitution back when we solved this using separability. So it makes sense, we should get the same result, but what I'm suggesting is, if we had just tried a generic e to the mx and plugged it in, we can actually go through some algebra to figure out what is the appropriate value of m that satisfies the equation. And all it requires us to do is basically solve this algebraic equation. And this algebraic equation is what we're going to call the characteristic equation. So in this case, AM plus B equals 0. So I guess really this line down here, AM plus B equals 0. If we can solve that, we can figure out what M looks like, the M that will satisfy the solution to the original differential equation. So let's extend this idea to a second order differential equation. So let's extend this notion to the second order version. Let's just try plugging in the same type of guess. So, for example, we've got our original equation, which looked like, where did I write? A y double prime plus by prime plus cy equals 0. And what I'm suggesting is, let's just try y equals, remember I said we don't need this constant out in front, it winds up canceling out, so let's just try e to the mx. Let's just try y equals e to the mx as our solution. If y equals e to the mx, then what is y prime and y double prime? Well, the derivative, y prime, will be m e to the mx. By chain rule, we'll pick up a factor of m, and when I take the derivative of this to get y double prime, I'll pick up another factor of m, and we'll get m squared e to the mx. And we'll plug these in, sub them into the ODE, to get the following. So here's the differential equation we're subbing them into right here. So it's going to be a times the y double prime term. So I'm going to have a times m squared e to the mx plus b times the y prime term. So b times this, b times m e to the mx plus c times the original y. So here's y. We've got plus c times e to the mx equals 0. And clearly, again, if I had put some constant in front of all of these terms, if we'd put de to the mx here, we'd have a d here and a d here. A d would show up in all of these, and again, we could cancel it out. So we don't need that extra constant. We can just try y equals e to the mx and get exactly what we're going for. They all involve an exponential term with the same power, e to the mx, so we can factor that out exactly as we did before. And we'll wind up with this, am squared plus bm plus c. And this tells me that the stuff in parentheses, am squared plus bm plus c equals 0, because the exponential itself can't be the part that's equal to 0. And as soon as we solve this for the appropriate value of m, we will have successfully solved the problem. So this is what we call right here, this is the characteristic equation, and it's very important. we can solve this. It's often, I'm going to call it the characteristic equation. Some books call it something like an auxiliary equation. So the auxiliary equation. But again, the words I'm going to use is characteristic equation. Just because that's how I first learned it. And we can do it to find the value of m. And once we have m, we know our solution. Our solution is just y equals e to the mx. And we can construct our solution by just knowing that once we have the value of m, we have our solution. So that's it. I just want to think now a little bit about what this might look like. So what do the solutions of this thing we're calling the characteristic equation look like? So solutions of the characteristic equation. Okay, so our characteristic equation we just wrote down as am squared plus bm plus c equals 0. So first things first, let me just make it totally clear. Let's relate this characteristic equation back to the original differential equation. So get this all on the screen here. Here's the differential equation that we were looking at. Here's its corresponding characteristic equation. You'll notice that the coefficients of the terms that show up in our differential equation match the coefficients that show up in this case of our algebraic equation down here. All we've essentially done is replaced m to whatever power corresponds to the order of that given derivative. So no derivatives here means we have an m to the 0th power. First derivative here, here's an m to the first power. Second derivative here, m to the second power. And we wind up basically replacing our differential equation with a algebraic equation that we can solve in a straightforward way. So you can jump basically straight to the characteristic equation from a differential equation by just copying down these coefficients. So that's the idea. Once you have those, how do we solve it? Well, in general, we're going to wind up with a second order differential equation. We're going to wind up with a quadratic equation, right? A second power equation. And we can always solve this using the quadratic formula. So if you'll remember, the quadratic formula says the solution to this is going to be negative this coefficient, so negative b plus or minus the square root of b squared minus 4ac, the whole thing over 2a. Right? This is just, again, quadratic formula. If you don't have it memorized, definitely time to commit it to memory. And this leads to different forms. So we have m. If you think about it, we're always going to wind up with basically two solutions from this thing. Well, not always. We'll talk about that in a minute. But in general, quadratics have two zeros, right? There's two different points where that parabola is going to intersect the x-axis. But the reality is we aren't always quite so lucky. We're looking for multiple solutions because we already know for a second order differential equation, I can construct the general solution as long as I can find two linearly independent solutions. And we can basically construct a linear combination of them to come up with the general solution to this. So for a second order equation, I need two solutions. And the nice thing is, again, the quadratic formula generally gives us two solutions, one corresponding to the plus sign, one corresponding to the minus sign. However, it's a little bit more complicated than that. So let's think about this. So if this term here in the square root, which is the piece that's allowing us to have multiple solutions, if it just gives us some positive number, we're in good shape. So if our b squared minus 4ac, if this term inside the square root is a positive number, then the square root of it will just be some other positive number, and we're taking the positive and negative version of that square root. and we'll just get two distinct values of m. So we'll do an example of this. If this is still unclear, we'll do an example in a minute. But if b squared minus 4ac is greater than 0, it's some positive number, we're in really good shape. We're going to wind up with two different values of m. We're going to wind up with an m1 and m2, and they're both going to be real distinct numbers. If, on the other hand, we wind up with our b squared minus 4ac being equal to 0, so what if you wound up getting 0 in here? Well, the square root of 0 is just 0, and I would wind up with m being equal to negative b plus 0 over 2a, and then the other solution would be negative b minus 0, the whole thing over 2a. And whether I'm adding 0 or subtracting 0 makes no difference. I only wind up with one solution. And that's going to be a problem because, again, for a second-order differential equation, we need two distinct solutions to construct our full general solution. So in this case, if that's equal to 0, we're only going to wind up with 1. m1 is our one solution, and it's real. It's going to be a real number, but it's a repeated root. Right? It's a repeated root. Doesn't show up. We don't get two distinct solutions. And for our third case, it's possible that the b squared minus 4ac could wind up being less than 0. And if it's negative, then when we take the square root of a negative number, what we're going to wind up with are imaginary solutions. And so in this case, we wind up with m1 and m2 with this part of the m1 and m2 being imaginary. This part will still be real, so we'll have a real part, we'll have an imaginary part. That means these two numbers are going to be complex, and because one involves a plus version of the imaginary part and the other involves a minus version of the imaginary part, they are in fact what we call complex conjugates. So m1 and m2 are complex conjugates. So these are the three cases, 1, 2, and 3. And if you think about what they correspond to geometrically, so let me just do this kind of off to the side here. This equation, as we just said, is basically a parabola. If I were to graph y equals the left-hand side of this as a function of m, we would get a parabola. And when we think about a parabola, a couple of different things can happen. So if this is our x-axis, or in the case of what we're doing over there, our m-axis, but I'll just stick to x's. These are the different kinds of things you can see happen. You can get a parabola that comes down and does something like this, goes back up, and in this case, we get two real distinct values of x as the solutions to when is the parabola equal to 0. So here's our basically the equivalent of, let's get it all on the screen at once. Case 1, m1 and m2 are real and distinct. So maybe this is m1 and this is m2. Here's our two real distinct solutions. But another shape the parabola can take is it can come like this. It can come dip down and just barely touch the x-axis and only have this one single 0 right here. This is the case where we get a real repeated root. It comes down and just barely grazes it. So this is case number 2. And then lastly, we could also get it so our parabola looks like this. In which case, it never makes it down to the x-axis. There are no real roots, and instead, the roots of this one wind up being complex conjugates. And so basically, if you think about these as case 1, case 2, and this one is case 3. In terms of what that parabola looks like, it leads to these different results here. So we're going to need to basically treat each one of these cases differently and figure out what solutions look like for each one of these. Okay, so let's consider each case separately. And then I'll make sure we also do examples of all of these so we can get a sense using real numbers of exactly what I'm talking about. So let's start with case 1. Let's clean it up. I like using those instead. So case 1. If M1 and M2 are distinct and real, then we have our two linearly independent solutions that we can use to construct the general solution. The first one, y1, looks like basically e to the m1x, and y2 is simply going to be e to the m2x, and these are our two linearly independent solutions. The general solution is always found by taking a linear combination of these. So y would be some constant, we'll call it c1, times y1, so c1 e to the m1x plus c2 e to the m2x. Here's our linear combination. C1 and C2 are constants, and it's a linear combination of the two linearly independent solutions. So this would be the general solution if M1 and M2 are real and distinct, case 1. We'll do an example of that in just a little bit. I want to go through all the cases hypothetically first, then we'll go through all the cases using concrete actual numbers. So case number 2, where M1 is real and repeated, the case where our parabola just comes down and just barely grazes the axis and then returns. So let's look at case number 2. So if M1 is real but repeated, then we only have one solution. Which is that y1 equals e to the m1x. How do we get our second solution? Well, luckily, we have a technique. If I give you one known solution, we can use reduction of order to find the second solution of a second order differential equation like this, a second order linear differential equation. So we are going to use reduction of order. Okay, so the first one is, let's just make this totally clear. Coming back to the whole equation here, right? The assumption is that b squared minus 4ac was equal to 0. That's the case that gave us this real repeated version. So what that tells me is basically if this part has gone to 0, the solution for what we're calling our m1 here is just going to be the negative b over 2a, because this part is now gone. So we know that m1 is equal to negative b over 2a. And again, that just comes from the quadratic formula where this term in the square root is 0, which is the assumption that we're working under when we get a real repeated case. So if this part goes to 0, m is just negative b over 2a. That's what we're starting with. So that means our solution, our y1, is e to the negative b over 2a times x. So this is our one solution. How do we find our second solution? Well, we can remember our formula from reduction of order. So from reduction of order, we can either go through the process or just, in this case, I'll just use the formula. But from the reduction of order process, we know that y2 is going to be equal to, you take y1 and you multiply it by this big, ugly, messy integral that's e to the negative integral of p of x dx, and we'll come back and talk about what that p is in a minute, over the y1 itself squared dx, where the p of x appears in the form of the differential equation where the leading coefficient is 1. So come way back up here. Here's the differential equation that we're trying to solve. If I divide everything in this equation by a, that's what gives me the p of x. So we're going to have y double prime plus b over a times y prime plus c over a times y equals 0. It was the original differential equation, and I divided everything by a. This term right here is what we normally think of as p of x, but in this case, I don't even need the of x because I know it's going to be a constant because both b and a themselves are individually constants. And this is what we were calling before q of x, but again, now it's just going to be a constant. So this is the idea. The p of x in this formula is the coefficient of the y prime term after we've divided through to make the leading coefficient a 1. So in this case, p is not a p of x, it's just a constant, and it's b over a. So let's plug all of this in. For now, we're going to get a big, ugly mess. So this gives the following for our y2. Try to get all of this on the screen at once, and I can hopefully write this. So y2 is equal to this mess where y1 is now this exponential. So it's going to be e to the negative b over 2a times a big integral of e to the negative integral of b over a dx. The b over a comes from what we found p to be. P is b over a. And then we're dividing that by y1 squared. Well, this was our y1, so it's going to be e to the negative b over 2a squared. E to the negative b over 2a squared dx. So this is our big, ugly mess that we're dealing with right now. The nice thing is you can see here we have an e to the negative b over a with an extra 2 in the denominator. Here we have an e to, after we integrate this, it's just going to be a negative b over a times x. So let's do that. So I'm going to have e to the negative b over 2a times the integral. I'm just going to solve this part to clean this part up. So this one's going to be e to the negative b over a times x. And in the denominator, I'm going to get e to the negative b over a squared. But what happens when you square an exponential? So basically, if you take an e to some power and then raise that whole thing to some power, all you need to do in this case is multiply the two powers. And so what we'll get after all of that is said and done is this is just going to be e to the negative b over a. Okay, so let's relate this all, and I can't forget my dx out here. So stuff is kind of getting cleaned up a little bit. We can try to clean this up again in more generality by, let's just, instead of having to carry this fraction around, let me just remind you. So remember, what we called this power before, the m1. m1 is what we said was negative b over 2a. So m1 equals negative b over 2a. So what does that mean this negative b over a is that keeps showing up? So if I write this, if I were to double this fraction, it would get rid of the 2 in the denominator, and I would get negative b over a, which is exactly what shows up here. So 2m1 is the negative b over a term. if I just double both sides. So cleaning this up just a little bit so I don't have to carry around these fractions everywhere. This first term is e to the m1 x. I drop my, remember, it's the full y1. I dropped my x here. So there should have been an x there and an x there. I need my x there. This other term is now e to the negative b over a times x, but negative b over a is 2m. So I now have the integral of e to the 2m1 times x. And down here in the denominator, and I also forgot my x here, and that when that x gets squared, we're basically good as well. So remember, we're still just multiplying this by 2. We still have multiplied it by 2. We don't need to like have this x be squared down here. When squaring this whole piece, you just multiply the two exponents. And so down in the bottom, I've also got an e to the 2m1x dx. And so this is a really complicated way of writing the number 1. And so this whole thing is e to the m1x times the integral of dx. Well, what is the integral of dx? It's just x. There we go. Okay. So cleaning it all up. So if we clean this all up, our y1 is generically e to the m1x, or in this case, e to the negative b over 2a times x. And y2 simply winds up being x times that same exponential, x e to the m1x, or cleaned up, x e to the negative b over 2a times x. So we could have done that, again, however you want to do it. I guess this would have been just as easy right here. I could have just said, oh, look, we've got e to the negative b over ax over e to the negative b over ax. Again, this fraction just simplifies to 1. And we just pick up an extra factor of x times the original y1 that we had. And so that's what we found here. Now I do have two linearly independent solutions. And the general solution is just some linear combination of those two. We're going to get that y is equal to c1 e to the m1x plus c2 times x e to the m1x. Here's our y1. Here is our y2. And each is multiplied by an appropriate constant. So that is what the general solution looks like in the case of a real but repeated root. And so let me box the other one as well. This is our real distinct root case up here. So here's case 1. Here's case 2. And then case 3 turns out to kind of be the ugliest case, but let's do that one as well. So case 3. Just remind you where we are. Go all the way back here. Right. Here are my 3 cases. M1 and M2 real distinct roots. That led to this solution. If M1 was a real but repeated root, that leads to this solution. And you can basically jump straight here. You don't have to go through all the work. You know that the equation will take this particular form. This is the form of the solution. And then our third case we're about to do, the third case is if b squared minus 4ac is negative, and so we wind up getting 2 complex conjugate roots, right? So they are going to be complex numbers. They'll have a real part and an imaginary part. So let's come back to case 3 and do that case in some detail now. Okay, so if our two roots m1 and m2 are complex conjugates, then basically what we would say is, let's say m1 looks like this. I'm going to pick a real part. We'll call the real part alpha, and we'll call the imaginary part beta. Right. We can figure out what alpha and beta are based on, again, the solution of our quadratic formula way back here. Here's what the real part will look like. Here's what the imaginary part will look like. It'll include those two terms, but it'll make more sense when we do this with real numbers. After you simplify all of that, you'll have some real number plus some imaginary number, basically with this coefficient here. So if that's what m1 looks like, m2, the complex conjugate, will be the exact same thing, but with a minus sign, because that's the only difference in the quadratic formula, right? It's plus or minus that square root of the negative number term, which will give us the plus and minus version of the imaginary part. So this means that we have two different solutions. Our two solutions are y1 equals e to the m1, so e to the a plus b or beta I times x, and y2 will be e to the m2, so alpha minus beta I times x. So these are my two solutions. To make things a little bit easier to deal with, I want to use something called Euler's formula, and this will make life a little bit easier on us. So hopefully you were introduced to this at some point. I know I introduced it in my trig class. I think I maybe mentioned it again in Calc 1, maybe it was in Calc 2, can't remember. So if you've never seen this before, this is a formula that can be derived in a number of ways. So this is sort of a little side note. This is something called Euler's formula. Euler invented a lot of things, so this is one of several things called Euler's formula, but this is probably his most famous formula. And it basically says the following. If you do e to the I times some theta, it turns out you can rewrite e to this imaginary power theta in the following way. It's the same as cosine theta plus I times the sine of theta. So this is Euler's formula. It relates exponentials with imaginary powers to sines and cosines that are, again, in this case, this is a complex number, right? It has a real part plus I, an imaginary part, times some, here's the imaginary coefficient, basically. If we do the equivalent for e to the negative I theta, all that's going to do is basically, it's the same formula, but we just swap everywhere that theta showed up with a negative theta. So that's the same as cosine of negative theta plus I times the sine of negative theta. But due to the even and odd rules, the even and odd properties of cosine and sine, we can use those even and odd identities to know that the cosine of negative theta, because it's an even function, is the same as cosine of the positive version of that same theta. So this is the same as cosine of theta. And sine is an odd function, so when you take the sine of a negative number, it's the negative of the sine of the positive argument. So all that happens is we flip this sign. So here's Euler's formula. Here it is extended to something that has a negative power. And I want to now basically find a way to rewrite what we've got written over here using these formulas to introduce some sines and cosines into these solutions. So we can rewrite these. So again, this is sort of just a side note. I'm not going to prove this. Proving this requires a bit of basically complex analysis. If you decide to continue your mathematical career longer and eventually take a complex analysis class, you will see this done very clearly in that class. But for now, we'll just stick to it as some magic formula that happens to be true. That's going to be really convenient for us to rewrite what these solutions look like, because I'd much rather not carry around these big, ugly exponents everywhere we go. So let's think about what we've got. So we can rewrite the solutions by breaking off e to the alpha x times e to the beta I x, and writing the e to the beta I term, the term that has the imaginary part, in this particular form. So we can rewrite the solutions. For example, y1 is going to be e to the alpha x times e to the beta I x, but that's going to be equal to e to the alpha x, right? This formula doesn't pertain to real powers, but it will modify this part. So essentially what I'm doing is I'm replacing what we called theta here. In this one, that's the x and the beta together. So this is going to be cosine of beta x plus I sine of beta x. So here's what y1 looks like. And here is what y2 would look like. It's similar, but remember, its only difference was it had a negative sign in front of the imaginary part, so it's going to be e to the negative beta I x. And we just saw what happens when we use the negative version of this. We get this expression down here. So I'm going to have my e to the alpha x, and I'm pulling that out, and I'm going to get cosine of beta x minus I sine of beta x. So here's y1, here's y2, written using Euler's formula. The general solution, as you'll recall, is some linear combination of these two pieces. So the general solution is y equals c1 times y1 plus c2 times y2. And when we do that for these expressions for y1 and y2, we're going to be able to actually do a little bit of work on this. So let's think of it like this. We're going to have c1 times our y1, which was e to the alpha x times cosine of beta x plus I sine of beta x. Good, so there is the way that we've written c1 times y1, right? Here's our y1, plus c2 not forget the real part here. So c2 times y2. So I need my e to the alpha x, which I've taken care of. And now I need my cosine of beta x minus I sine of beta x. So here's what this looks like. But I'm going to, again, try to clean this up by doing a little bit of rearranging some terms here. So one thing that can happen is basically I can try to find some clever ways to kind of combine these. I can pull out an e to the alpha x from both of these. That'll make life a little bit easier. So let me pull out an e to the alpha x. This is all just, everything I'm doing now is basically just some algebra here. And we've got now, let's see here. I've got c1 cosine of beta x plus c1 times I sine of beta x plus c2 times cosine of beta x minus c2 times I sine of beta x. So all I've done is basically distribute the c through to these two pieces. Same thing here, c2 going through to these two pieces, and I've factored the e to the alpha x out of the whole thing because it showed up in all of these terms. And what I want to do now is basically rewrite this so that I don't have all of these, some parts being imaginary, some parts being real. We can actually be kind of clever in the way that we combine and rename these terms by noticing that we haven't actually picked C1 and C2. C1 and C2 just need to be constants. That's our only requirement. It doesn't even specify that they have to be real numbers. They could be some complex or imaginary number if that so suits us. So here's the idea. I want to try to rewrite all of this without all of these i's sitting around. I want real solutions. Our original differential equation, which is oops, didn't mean to move that guy. Undo that move altogether. Okay. Whoa, too far. Here's the differential equation that we were trying to solve, way back here. It is a real differential equation. A, B, and C are presumed to be real constant coefficients. We're expecting real solutions. The first approach that we took gave us real solutions. The second approach that we took gave us real solutions. This third approach better give us real solutions. And so this is why I'm wanting to get rid of the I that shows up right here and right here. So how can we do that? The idea is that these constants themselves, what I'm calling C1 and what I'm calling C2, those values themselves can potentially be imaginary or some weird combination of things if it's going to help eliminate I from this. So that is what I'm claiming. So I'm going to, by a careful way of rearranging things, I'm going to pick basically C1 plus C2 to be just some new coefficient. So basically, here's what I want to do. E to the alpha x. Let me group the ones that involve basically that are already real. So this term is already real. This term is already real. This one has an I. This one has an I. So these two terms are already imaginary. So let me group these two that are real. It's both the cosines together. What I'm going to do is write this as, so I've got C1 plus C2 cosine of beta x. Right? That is this term and this term grouped together, and all I've done is factor the cosine term out. So it's just the C1 here plus the C2 from right here. And then separately, I'm going to group these two terms together that are the imaginary terms. And in this case, it looks like I have that C1 minus C2 times the I times the sine of beta x. So those are grouped together. So again, I've grouped this guy and this guy. They gave me this. And I've grouped this guy and this guy to give me this. And all I've done is factor out the common parts. I factored out the I, factored out the sine of beta x over here. What I'm going to do now is just say, let's let C3 be some new constant. C3 is going to be C1 plus C2. And I'm going to let C4 be a different new constant. C4 is going to be C1 minus C2 times I, some other new constant. And I very specifically picked that C3 is this coefficient sitting in front of the cosine term, and that C4 is this whole coefficient, including the I, sitting in front of the sine term. So basically, I've picked C4, assuming C1 and C2 were real numbers, which they were over here. This C4 turns out to be an imaginary number, so that I can assume that this whole term winds up being real. And that's kind of the idea. We're going to drop the I dependence here, again, because again, we haven't specified C1 and C2. These are the constants that come from having to integrate twice. These are the C1 and C2 are essentially the constants of integration that we get when we solve this differential equation. Until we plug in an initial condition, they can be anything we want. And so I've picked them to be these convenient combinations for the time being. That's totally fine. So we get, after this is all said and done, that our general solution is going to be y equals basically e to the alpha x times c3 cosine of beta x plus c4 sine of beta x. And this is our general solution. This is exactly what I've got written right here. And I've just simplified these coefficients down and called this C3, called this C4. So here is our general solution. And furthermore, going way back to what the original presumption was of our form of our M1 and M2, basically once we know what our complex conjugate roots are that are values of M, we know the alpha and beta. Once we know alpha and beta, here's where I plug in alpha, here's where I plug in beta, and this is the general solution. So we have the general solution. Is the second we find the values of M and know what alpha and beta are, we can just plug into this formula, and that's our general solution. You don't need to go through all the interim work. Basically, once you have this, you can jump straight to here and skip all of this in between. And that's what I'm expecting you to do going forward. We've justified it here. We don't need to reinvent the wheel every single time we do one of these problems. One thing I want to point out is that's kind of important. Note what happens if alpha is 0. So if alpha equals 0, what that means back up here is that if alpha is 0, then our solutions for our values of M are pure imaginary. Right? We would only have this beta term, and so we'd have a pure imaginary. The real part would be 0. If the real part is 0, then this exponential is gone, and we're only left with this part because e to the 0 is simply 1. Y would be equal to c3 cosine of beta x plus c4 sine of beta x. So in this case, if the real part is 0, we get pure sines and cosines. So pure sine and cosine functions. No exponentials. If there's an alpha and a beta, so if our numbers are complex, we get a combination of both. We get an exponential, and we also get sines and cosines. So we have a part of our function that's either growing or decaying, depending on whether alpha is positive or negative. And then we have sines and cosines. And what is the behavior of them? Those are oscillations. And so in general, again, alpha is negative b over 2a. The beta term is the square root. So basically, this is, again, coming way back from, where did I write it? Here, quadratic formula, right? So our real part is the negative b over 2a. The imaginary part, we've assumed this is negative, so I could basically factor a negative sign out of it, and the square root of that negative 1 would be the I explicitly. So this is where you'll see I'm going to flip the order of these two terms to ensure that what shows up in the square root is now positive, and assume that we've already factored out the negative 1 that made it negative to begin with, because we're on this case. So let me write this down. Beta is going to be the square root of the 4ac minus b squared over 2a term. So that's it. And again, the idea is that this term right here, so what I was trying to say is this is positive, assuming that the b squared minus 4ac is negative, which was our assumption that led to us getting a complex number anyways, right? So I basically factor the negative 1 out. So basically, when will alpha be equal to 0? How do I make this term be equal to 0? Well, the only way I can make this term be 0 is by letting b itself be 0. And what does that mean back in the original differential equation? So what it means is our ODE is actually just a y double prime plus, remember, we're assuming now b is 0 if alpha is 0, plus cy equals 0. This is the form of a differential equation, missing the first derivative term, so no first derivative, that leads to pure sine and cosine solutions. So basically, if alpha is 0, that leads to pure sines and cosines, because again, this exponential just becomes a 1. But when does that occur? Well, that occurs when here's our alpha expression. This can only be 0 if b is 0. When b is 0, it means the original differential equation is missing that middle term where the b coefficient normally sits. So we only wind up with a y double prime term and a y term. This is what leads to pure sine and cosine oscillation terms. Okay, so let's do some real examples with some real numbers of each of these three cases that we've just gone through. I want to gather up all of my examples here. So let's do a bunch of examples. Okay, so let's try this one. Let's do let's see here, 2y double prime minus 2y prime minus 12y equals 0. Okay, so find the general solution. Okay, so the first thing I want to do, just to make life easier, is whenever possible, divide out by any common factor that shows up. In this case, all of these are even. I can just divide them all by 2, and we could rewrite this equation as y double prime minus y prime minus 6y equals 0. Same differential equation. We've just simplified it a bit. And in general, that's the goal. All of these differential equations, it's always easier if you make the leading coefficient a 1 before you start doing the extra work. What we would do is now try our solution. So let's try y equals e to the mx. And that would mean that y prime would be m e to the mx. And just so you know, I think in your book, they might not use m. I feel like they might use r, but it's the same idea. Whether you're using m, r, any constant we want, doesn't really matter. So here's what y prime looks like. Y double prime will be m squared e to the mx. We can plug all of these in just to verify. So plugging in, we'll get y double prime, so m squared e to the mx, minus y prime, so minus m e to the mx, minus 6y, so minus 6 e to the mx equals 0. We can factor the e to the mx out, and we are left with the characteristic equation, m squared minus m minus 6 equals 0. So the characteristic equation, and again, going forward, you don't need to necessarily do this work every time. If you absolutely can, I'd recommend doing it a couple of times at the beginning, just make sure that you've got the process down. But you should always wind up with a characteristic equation that takes a very similar form to the differential equation itself. The characteristic equation is, in our case, m squared minus m minus 6 equals 0. M squared corresponding to this term, minus m corresponding to this term, and then just minus 6 corresponding to this term. And so how do we solve this? Well, we can either use the quadratic formula or we can try to factor it ourselves. In this case, I'm looking for two numbers that when I multiply them together, I get a negative 6. And when I add them together, I get a negative 1. And to me, that seems like that's going to be an m minus 3 and m plus 2. I think that factors appropriately, so let me just double check. M squared, good. I'll get a plus 2m and a minus 3m. The plus 2 and the minus 3 will give me a total of minus 1m. and then the last number will be the negative 3 times the 2, which indeed gives me the negative 6 that I'm looking for. So here we go. In this case, the values of m are either 3 or negative 2. And so the general solution is the following. We've got two real distinct values. The general solution is that y is going to be equal to c1 times e to the this particular mx, so c1 e to the 3x, plus c2 e to the negative 2x. Those are my m1 and m2 values that we're plugging in. So here's the general solution to that equation. Done, just like that. Let's do another example. So the real distinct case is very easy. That's the one that we just did. What about a case where we don't get real distinct solutions? Let me think. Let's do y double prime minus 8y prime plus 16y equals 0. So here's another one. What are we going to get in this case? Well, again, what is the corresponding characteristic equation? So I'm going to skip this step of finding the derivatives, plugging them in, factoring stuff out, and just know the characteristic equation for this thing is going to be m squared minus 8m plus 16 equals 0. So basically, swap out the double prime for an m squared, the y prime for an m, the y for just a 1, and that gives you your characteristic equation. Same thing, we can try to factor this and figure out what the result is going to look like. I'm looking for two numbers that multiply to give me 16, add to give me negative 8, and that looks like that's going to be m minus 4 times another m minus 4, so m minus 4 squared, which implies that we only get one solution, m equals 4. So in this case, we've got a real but repeated value. So here's our real repeated root. And we can go through all the work if we want, but I know right off the bat the solution to this is that one of the two solutions looks like e to the 4x, and the other, y2, is going to be x e to the 4x. We pick up a factor of x. This came from, again, where's that x coming from? That x is coming from right here. Here's the value of x. We pick up this factor of x when we do a reduction of order using our one known solution, right? We only had one solution and we did reduction of order. This was in total generality the way that we did it here, and you always just pick up an extra factor of x. And so I'm just jumping straight to that and saying, here's what the second solution looks like, x e to the 4x. That means that the general solution is just a linear combination of these. It's going to be y equals c1 e to the 4x plus c2 times x e to the 4x. And just like that, we can be done solving this problem. The last case is probably the ugliest or most difficult. Let's do an example of that last case. And while I'm at it, let's throw in some initial conditions just so we can see kind of how this is going to work when we actually need to solve for C1 and C2, because I haven't done that in these last two cases. So let's do an example that looks like this. I'm going to do 16y double prime minus 8y prime plus 145y equals 0. And I'm going to give the conditions that y of 0 is equal to 2. Actually, let's do negative 2. And y prime of 0 equals 1. Okay, so now I have an initial value problem. because I've specified the initial value of both y and y prime. And here is the equation that we're dealing with. This is not one that I can just factor right off the top of my head. I can see, oh, it looks like I'm going to be able to cancel an 8 and an 8 here, but then I get to this one and it's not even, so I can't even cancel a 2. So I don't even know how to simplify this and make these coefficients nicer. Let's just jump straight to the quadratic formula and try to figure out what the value of m is. So our characteristic equation and I actually really like to, I'm using m now, but I also in the past have used, you may see this in my homework solutions, if I use lambda instead of m or r, these are kind of the three most common letters that you'll see used, m, r, or the Greek letter lambda. So you could write this characteristic equation. It's hopefully not scary, it's just a different letter, but it's still just, right? You could see it written as lambda squared minus 8 lambda plus 145 equals 0, or m squared minus 8m, sorry, I missed my 16. 16 lambda squared minus 8 lambda plus 145 equals 0. So again, just bring these coefficients down and replace the y double prime, y prime, and y, respectively, with lambda squared, lambda, and 1, or m squared, m, and 1, or r squared, r, and 1. So all of these are totally equivalent. We've just changed the variable that we're using, r squared minus 8r plus 145 equals 0. So just all I'm saying is sometimes I interchange, I'll use m, sometimes I'll use lambda, and I think, actually not sure if it's this book or a different textbook I was using at one point uses r, but all of these are common ways of writing out these characteristic equations. So just don't get flustered when you see a different letter being used for the characteristic equation. They're all the same thing. And if you do have any questions, let me know, and I'll try to be more consistent. But I think I've already written up the homework solutions, and I don't remember what I used. I think there's a good chance I used some lambdas in there. So that's why I wanted to show you this now. So in this case, let's just say that hypothetically we're going to use this version for this problem. Let's use the lambdas. In this case, what am I going to get for lambda? Well, lambda will be equal to, right, negative b. So in this case, we can't, we've got our b is basically this number right here. So negative b, can't forget to cancel those. I'm going to get positive 8 from that. So you can think of it as a negative 8 plus or minus the square root of b squared. So negative 8 squared. I'll just write that as a 64. We'll do the square in our heads. Minus 4ac, so minus 4 times a, which is 16, minus times c, which is 145, all over 2a. So here's this big mess. I'm going to have positive 8 plus or minus the square root of, what is this? So this is going to be 64. 4 times 16 is also 64, so I have 164, and then from that I'm subtracting 145 64s. So that's going to be, I guess we can just do this on the calculator. Let me pop up a calculator here real quick. So 4 times 16 times 145. 9280. So 64 minus 9280, whole thing over 32. So we're doing 64 minus this answer that we just found. Gives us negative 900 or 9,216. Well, let me take this. I can't even remember if the calculator will do this. It'll give me the I or not. Nope, non-real answer. Okay, let's go back to it, and I just want the square root of that 9,216. Okay, 96. So this is going to be 8 plus or minus 96i over 32. Whew. Ugly, but that 8 over 32 simplifies to a 1/4, plus or minus 96 over 32 simplifies to 3. So there is my complex conjugate pairs of the roots of my characteristic equation. So in this case, what I'm calling lambda. Let me close this, open this back up. And so we have our value of alpha and beta. So this is our alpha, and this coefficient right here, not including the I, is our beta, right? We always kept the I separate from the beta. So this means that our general solution as soon as we've got that, our general solution takes the form y equals e to the alpha t, so e to the 1/4 t, times c1 cosine of beta t, so cosine of 3t, and I'm using t instead of x, and I guess I used x in all the previous ones. I'm assuming that we're doing t here just because that's usually what I think of when I think of an initial condition. So nothing here specified that we were using time, but that's just often what I kind of default to in my mind whenever an initial condition is prescribed like this. So you could obviously use x instead of t as well. Hopefully that is not confusing. I'll try to make it explicit here, and we're assuming that y is a function of t as sort of the assumption I'm making in this problem. Okay, so there is the cosine of 3t plus some other constant times the sine of 3t. And where am I getting this general form of our solution? It's simply coming from right here. Here's the general form, e to the alpha x, some constant times cosine of beta x, plus some constant times sine of beta x. And again, I used x here, I'm using t down there. Change the name of the independent variable, but that doesn't make any difference. As soon as we know alpha and beta, we have our general solution form. So here's my alpha and beta, here's the general solution form. So this is what the general solution looks like. Now let's solve for the constants, C1 and C2. So now plug in the initial conditions. Well, one of them is that we know that y of 0 is equal to, what did I say, -2. So what is y of 0? Well, that's going to be e to the 1/4 times 0 times c1 cosine of 3 times 0 plus c2 times the sine of 3 times 0. And that's supposed to be equal to -2. Well, the sine of 0 is 0, so this whole term is 0. This term, the cosine of 0 is 1, and e to the 0 is 1. So what I get from this is basically just c1 is all that survives. 1 times c1 plus 0. And so c1 must be equal to -2. That means that y is now e to the 1/4 t times -2 cosine of 3t plus c2 times the sine of 3t. So we've solved for one of the two constants. Now I need y prime of 0, so we need y prime. Y prime is going to be ugly because I've got to do product rule on this thing, but that's just what we're going to have to do. So let's do our product rule on this thing. Y prime, I'm going to get first times the derivative of the second plus second times the derivative of the first. So I'm going to get the first times the derivative of the second. What is the derivative of cosine of 3t? Well, I have this negative 2 that's going to be sitting there, so negative 2. What's the derivative of cosine of 3t? The derivative of cosine is negative sine. So I'm going to get, and I'm going to also pick up by chain rule an extra factor of 3. So I'm going to get negative 3 sine of 3t plus, here's our C2, pull that out. What's the derivative of sine of 3t? It's going to be cosine of 3t with an extra factor of 3. So 3 cosine of 3t. So here's my first times the derivative of the second plus the second times the derivative of the first. And the derivative of the first will just be 1/4 e to the 1/4 t. And I just need to copy the original down. So there is what y prime looks like. So what is y prime of 0? Well, when I plug in 0, again, this will become a 1. So I'm going to have e to the 1/4 times 0. This, when I multiply through, will be a positive 6. So we'll have 6 times the sine of, we'll just call it whatever, 3 times 0, plus 3c2 times the cosine of 3 times 0, plus 1/4 e to the 1/4 times 0 times negative 2 cosine of 3 times 0 plus c2 times the sine of 3 times 0. So all I've done is plug in 0 into this everywhere that t showed up, and that whole thing is supposed to be eventually equal to 1, I think? Yeah, y prime of 0 is 1. So let's simplify it and then eventually set it equal to 1. So this term simplifies to just a 1. We have a sine of 0, which is 0. So I have 1 times a 0 plus 3c2, and the cosine of 0 is 1. So there's that term. Plus a fourth, because this exponential will become a 1, but I have a 1/4 multiplying it, so I'll have a 1/4. This cosine is going to give me a factor of 1 times this negative 2. We'll just leave me with a negative 2 there. And over here, the sine of 0 is going to be 0. And that whole thing is supposed to be equal to 1. So if we multiply through, I've got in fact, let's save this equals 1 for the end. So I've got 3c2, a quarter of negative 2 is going to be minus a half, and that's what's supposed to be equal to 1. So if we add a 1 to both sides, sorry, if we add a 1/2 to both sides, I'll have that 3c2 is equal to 3/2. Divide both sides by 3, and we'll get that c2 is equal to a half. Whew. So we get that y is equal to, coming back to all of this, c1 was negative 2, c2 is a half, so I just need to plug into this equation with those particular values of c1 and c2. So it's e to the 1/4 t times negative 2 cosine of 3t, oops, negative 2 cosine of 3t plus 1/2 sine of 3t. And if you want to write them out separately, that's totally fine. You could leave it like this. You could write it as negative 2 e to the 1/4 t cosine of 3t plus 1/2 e to the 1/4 t sine of 3t. However you want to write it. You can keep it factored. You can distribute. 6 of one, half a dozen of the other as far as I'm concerned. So just know that honestly the hardest part of a lot of these problems is the algebra that you're going to have to do to simply plug in the initial conditions, because you're going to have to be taking derivatives of, in some cases, these complicated expressions that involve both exponentials and sines and cosines. These are kind of the worst case scenario problems. Generally speaking, taking a derivative of something like this is fairly straightforward. So plugging in initial conditions to a problem like this, where you have the real distinct roots, is not too bad. Plugging in to find initial, or basically plugging in initial conditions into a problem like this is only a little bit worse, because you do wind up having to do product rule on this term. That's the x times the exponential. But by far the worst is these problems that involve exponentials and the sines and cosines, and having to plug in there. Okay, we're almost done. The last thing that I want to just mention is that there's really two cases that are worth knowing kind of off the top of your head. So back to general theory stuff. There are two cases just worth knowing, pat. Off the top of your head. One of them looks like this. Y double prime plus k squared y equals 0. And one of them is y double prime minus k squared y equals 0. Okay. In these two cases, basically you're going to wind up, so if you use this and went and basically solved for your characteristic equation, you'll get lambda squared plus k squared equals 0 here, or lambda squared minus k squared equals 0 for this one. And whether you want to use lambda or m or r or whatever, it doesn't matter. But these lead to the following two solutions. In this case, you'll wind up having basically a repeated root. So you will find that k is your, basically ik is your repeated root. It shows up, and it's purely imaginary. And it leads to pure sine and cosine solutions. So it leads to pure oscillations. So you get C1 cosine of kt or kx plus C2 sine of kx. So, and in the other one, you're going to get just exponentials, right? This is the difference of two squares, basically, in your characteristic equation, and you'll wind up with C1 e to the kx plus C2 e to the negative kx. And so even though these two equations look very similar, they lead to totally different solutions. One has solutions that are purely exponentials, a growing exponential, a decaying exponential. And the other one has pure sines and cosines, meaning the solution here oscillates. The solution here does not oscillate. So whenever this coefficient here is a positive, a plus, so if you don't notice again, the y prime term is missing, so we only have y double prime and y. If you have a plus term, because the k squared obviously has to be positive, so this term, the plus k squared, is a positive coefficient here. Whenever you have a positive coefficient in your y double prime plus some positive number times y, you will get pure oscillations in your solution, sines and cosines. So basically, if it's positive, meaning this term right here, if it's positive, oscillates. And if it's negative, right, this coefficient will be negative, never does oscillate. So this was the kind of little rhyme or mnemonic device I used to memorize these. These show up a ton. So if it's positive, oscillates, negative never does. Positive leads to pure sines and cosines, negative never does. It leads to pure exponentials. But these types of equations will show up a ton in practice going forward, especially if you ever take a partial differential equations class. These expressions show up all the time, and if you know them off the top of your head, it makes your life so much easier. The last thing I will say is that basically the same approach that we've just used for both first and second order ODEs. So for second order constant coefficient problems, extends to higher orders. And what do I mean by that? I mean the approach where we guess e to the mx, or e to the lambda x, or e to whatever x, or t, if you're using t's. So basically, right, plugging in our general guess for our solution of this form into the differential equation and getting a characteristic equation out of it. So for example, let's say we had the following. Maybe I've got y triple prime plus 2y double prime minus y prime minus 2y equals 0. So this is third order. If we try y equals e to the lambda x, or e to the mx, or e to the rx, or whatever version you prefer, we'll get the characteristic equation that looks like this. Characteristic equation. The characteristic equation in this case will look like lambda cubed, or m cubed, or again, whatever letter you want to use. Let's stick to m with this one. So we'll get m cubed plus 2m minus m, minus 2m squared minus m minus 2. I think I got that right. We can notice that m equals, and that's equal to 0. There's our characteristic equation. You can basically factor this one by grouping. So factoring cubics is always a pain in the butt unless you get lucky. In this case, I noticed that if I group the first two and then I group the second two, which you could think of as minus m plus 2 equals 0, I can factor out of that first one, I can factor an m squared out, so I get m squared times an m plus 2 minus a 1 times m plus 2 equals 0, which means that what we've really got is m squared minus 1 times an m plus 2 equals 0. This is a difference of squares, so we get m minus 1 times m plus 1 times m plus 2 equals 0. So m is equal to positive 1, negative 1, and negative 2. So the general solution is, in this case, because it's third order, we know it's going to be a linear combination of 3 linearly independent solutions, and those 3 linearly independent solutions correspond to the 3 roots that we just found. So I'm going to wind up with y equals c1 e to the x plus c2 e to the negative x, corresponding to the positive 1 and negative 1, and lastly plus c3 e to the negative 2x. And that's our general solution. I'm not going to give you a lot of higher order differential equations that are constant coefficient because they're the same idea with just worse factoring, worse algebra. You just need to know how to be able to factor cubics or quartics and so on, and that's just more work without being much more interesting in terms of like the fundamental idea behind what's going on. Also, most of the applications that we're going to consider only involve second order differential equations. So just know that you can extend this idea to higher order differential equations, but you probably won't see many of these. Certainly not something I'm going to put on an exam. So anyways, get good at doing these. Get comfortable jumping straight from basically finding your roots of your characteristic equation and jumping straight to the solution. So basically memorize the forms of the solutions in our 3 cases so you can jump straight to them. And then just know that you need to be careful with algebra in these problems. Algebra is the one thing that screws people up here. So don't be careless. Make sure that you're careful with your algebra, and these problems turn out to be pretty easy. But they're going to be a basis for all the stuff we're going to do going forward. So make sure you get good at these before we move on.